Hi there. In this video we're going to talk about phase change and latent heat. This is fifth in the series of videos on calorimetry. So assume you have a vessel where you have a block of ice, and this block of ice is at, let's assume, minus 50 degrees Celsius, and you want to melt this ice, so you heat with the help of candle, and this candle is giving heat at 1 calorie every second. Alright, so now what happens to this ice? Let's analyze what happens to this ice. So first, the ice is at minus 50 degrees Celsius. It becomes ice at 0 degrees Celsius at some point. So you have ice at 0 degrees Celsius, and at this point it just starts to melt. Now the heat which is at this point between minus 50 and 0 degrees Celsius, the heat absorbed is given by mc delta T, and the mass is, let's assume that the mass is 1 gram. So 1 gram into 0.5 calorie per gram Kelvin into 50 Celsius or Kelvin, doesn't matter because it's delta T. Alright, so that's because you hear delta T 50 Kelvin. Alright, so your Q would be 25 calories. Alright, so now from here, ice at 0 degrees, it has to get completely converted into water. This is water at 0 degrees Celsius. So please note that at this, as this happens, your delta T is 0. There is no change in temperature because it's ice at 0 and water at 0. You may be wondering why water at 0 degrees Celsius and ice at 0 degrees Celsius, what is the difference? And if you go think a little bit deeper, we know that temperature is same, so we know that average kinetic energy is same for 0 degrees ice and water. So average kinetic energy of molecules. Now what is different is the hydrogen bonds. In case of water, these hydrogen bonds constantly break, and they form with another molecule, and they break and they form with another molecule, and so on, and that gives it a liquid state. But in ice, that doesn't happen. The hydrogen bonds, all the bonds, they remain as it is in a very crude way. Alright, so now to change the state, there needs to be some energy that needs to be given. So the energy that needs to be given to change this state is called the latent heat of melting. So the latent heat, or rather we can say that for melting, right? And that is equal to, it's given by M into L for ice, and this is called, or we don't call it ice, we call it L of fusion. This is called specific latent heat of fusion. What this means is, and this value is about 80 calories per gram. what this means is for every gram you need to give 80 calories, so that for every gram of ice you need 80 calories to convert it into water. So in this particular case, we have 1 gram into 80 calorie per gram, and that is 80 calories. So that's the amount of energy you need to give for converting it from 0 degree ice to 0 degrees water. And latent heat of melting is the amount of total energy required to convert. So if you have 5 grams of water, the latent heat would be 5 into 80. Latent heat of melting would be 5 into 80, that is 400 calories for 5 grams. All right, now with this, from here the water at 0 degrees Celsius becomes water at 100 degrees Celsius. And for this we know that delta Q is given by mc delta T. Here the mass is 1 gram, C of water is 1 calorie per gram Kelvin, into delta T is 100 degrees Celsius or 100 Kelvin, doesn't matter as it's delta T. So this is 100 calories. And finally the water changes its state to become vapor. So this was D, and this is state E. Now here again we see that this is water at this is vapor at 100 degrees Celsius. So we see there is no change in temperature. It's just that the hydrogen bonds are breaking in the water, and they become vapor. So this stage we call it as the heat that needs to be given here is called latent heat of vaporization, and that's given by M into L vaporization. And this is nothing but this is called specific latent heat of vaporization, and the value for water is 540 calorie per gram. So in this particular case, this is 1 gram into 540 calorie per gram, that is 540 calorie. That's the amount of energy that you need to give. All right, now if you have to plot this in terms of a graph, the graph would look like this. On the x-axis you have the time, and on the y-axis you have the temperature. Now A to B we saw was, if assuming that this is for 1 gram of ice is where we start, so we saw that this one was delta Q is mc delta T, and here we found it was about 25 calories of energy that needed to be given, because this is 1 into 0.5 into 50 degrees Celsius, just now that we calculated. And this would be M into L, and that's 80 calories. And here would be mc delta T, that would be 1 into 100 calories. And from D to E we just calculated that this is M into L of V, and this is L of F, fusion and vaporization. So that here we call it latent heat, and here also of melting, and here we call it latent heat of vaporization, and that is 1 into 540 calorie per gram, that is 540 calories. Now it's important to understand this word latent means, in Latin it means hidden. Now why do we call it the hidden heat? Because obviously we don't see any rise in temperature between D and E. So this is kind of a hidden heat, and that is why the word latent heat. And so, you know, same thing happens between ice at 0 and water at 0. So there's no change in temperature, so that's why we call it hidden. All right, so with this graph, we call this the heating curve of water. The specific latent heat of fusion is 80 calorie per gram. This is also equal to 80 into 4.2 joules per gram, and that is 330 joules per gram. It can also be written as 330 kilojoules per kilogram, or equal to, this also can be written as 330 into 10 power 3 joules per kilogram. So you can try out all this conversion yourself, but it's important to remember these values in joules and kilojoules, etc. This is not in your syllabus, the vaporization, but still it's good to know. So vaporization is 540 calorie per gram, and this is also written as 540 into 4.2 joules per gram. That's 2268 joules per gram, or 2268 kilojoules per kilogram. We know that the ice is usually less dense than water. So what that means is, if you have a glass of water, most of the ice would be underwater. Reason is the ice has approximate density is 0.917 grams per centimeter cube, which is less than the density of water. So let's assume, you know, we are taking 1 gram of ice. 1 gram of ice, the volume would be 1 divided by 0.917 centimeter cube. This is 1.091 centimeter cube. Why did I say this? That's because I know that 0.917 gram is 1 centimeter cube. So 1 gram would be, this comes from the density. This comes from the density. So I can say 1 gram is this much. So what does this mean? This means that if you have ice of 1 gram, which it is 1.091 centimeter cube, and as you melt this into water, 1 gram water, the weight will not change, but the volume will change. The volume will be 1 centimeter cube, because density of water is 1 grams per centimeter cube. So we can say that density decreases on melting. The second important thing to remember is the impurities like salt decrease melting point of ice. So let's see what we mean by that. So if you have ice and you mix water and salt and you make it into an ice, let's say this by adding salt, the melting point it reduces to minus 22 degrees Celsius, or approximately minus 22 degrees Celsius. So now what are the uses of this? We use this property to freeze mixtures. So we call this, we use this kind of ice as a freezing mixture. In kulfis, also we use it to freeze fish and so on. Freezing fish and so on. Let's see some consequence of high specific latent heat of fusion of water. The first one is slow melting of ice in glaciers, etc., or mountains. Because a lot of heat needs to be absorbed for it to convert to water, so you will see that it holds up as ice for a long time. The second one is lakes do not freeze all at once, because it takes a lot of time to remove the heat from the water. The same energy, which is 80 calories per gram, it needs a lot of time to remove that much heat from the water so that it can become ice. Associated with this is also the fact that after winter, as ice melts, it makes surrounding very cold, because all the heat of the surrounding is absorbed by the lake for it to melt. So that makes the surrounding, any area near the lake, really cold and freezing. The same is true immediately after a hailstorm. As the ice ball melts, it makes surrounding very cold. And so it is true when you make a cold drink. A block of ice can cool down water much more than water at 0 degrees Celsius. So ice is very effective in cooling down your drink. So with all this in mind, let's move to the final list of checkpoint questions for this chapter. Here are the list of checkpoint questions. I hope this video was informative. See you on the next one. Ciao.